Chapter 1 begins with significant figures, and you have to be very careful as you try to solve significant figures problems. Remember, you're going to watch two things. You don't just count significant figures. If you are multiplying and dividing, if you're doing multiplication and division only, then yes, you ask, how many sig figs are there? How many sig figs? And you go with the fewest number of sig figs. However, if you're adding and subtracting, there's a different rule, and this is where most students miss this kind of problem. Adding and subtracting, the rule is you have to ask how precise is each measurement, because you're limited to how precise each measurement is. Now, this first question is an example of what people get into trouble with. Whenever they see this, they see you're going to subtract the mass of the beaker alone, 73.8 grams, from the mass of the beaker containing the sample, 75.652 grams. How many sig figs should be reported for the mass of the sample? Now, if this were a multiple choice test, then there would be these choices, 1 sig fig, 2 sig figs, 3 sig figs, 4 or 5 sig figs. And what would you choose there? Well, you have to be careful. Don't just look at the numbers, and too many students will look at this and say, this has 3 significant figures, this has 5, and since this has 3 sig figs, that must be the answer. That's the incorrect way to approach this kind of problem. In order to solve this question, what you have to do is you have to actually do the calculation. So when we set up the calculation and do it, we're going to say 75.652 grams, and we're going to subtract the mass of the beaker alone, and I'll line this up vertically the way that we learned to add and subtract back in 2nd or 3rd grade, 73.8 grams. Now, whenever we do this, here's what our calculator gives us. It gives us 18.52 grams. That's the calculator answer. I'll put this in brackets to indicate that that's the calculator answer, is not necessarily the correct answer. That should be 1.852. I looked at my calculator wrong. That's 1.852. And when you ask how, we're subtracting here, so we don't count significant figures. We have to ask how precise is each number. This number is precise to the 1,000th place. This second number is only precise to the 1/10th place, and so the answer can only be precise to the 1/10th place. It's not precise to the 1,000th place. It's precise to 1/10th place. If you line this up vertically, and I see that I messed up by writing this way, that I did 1.852. If you line this up vertically, then you'll see that the best answer that you can get is 1.8 grams. It's only precise to the 1/10th place. And so the correct answer for this is there will be 2 significant figures. Notice that even though one number had 3 significant figures, one had 5, when we subtracted them, we ended up with fewer significant figures. Now, the important thing you have to notice then is anytime you add or subtract, it's easy to make a mistake with significant figures. So you have to take your time, and with adding and subtracting, ask how precise is it. If all you're doing is multiplying and dividing, then all you have to do is ask how many significant figures, and you go with the least number of significant figures. Look at problem number 2. Problem number 2, and I'll go ahead and circle this answer. This has 2 sig figs. 2 sig figs is the answer. Look at problem number 2. Problem number 2 is a combined problem. In a combined problem like this, we have to go one step at a time and apply the appropriate rule at each step. And so when we do this, the first thing we'll do is we'll subtract what's in the numerator. So 12.32 minus 12.22. And now here's part of the problem. When you do this in your calculator says 0.1. 0.1. It just reports it this way. And yet when we subtract, we have to ask how precise is each number. And this number is precise to the 1/100th place, and this number is precise to the 1/100th place. So the numerator will be precise to the 1/100th place. In the denominator, when we divide by 3.97, then the next question that we ask, we're going to divide. We ask how many sig figs. Well, the numerator, and here's where you have to be careful, the numerator has 2 significant figures. When you subtract this, and we are limited to the 1/100th place, then there's 2 significant figures. 2 significant figures divided by 3 significant figures is going to give us 2 significant figures. Our calculator answer is 0.0251887. That's the calculator answer. But the best answer then, with 2 significant figures, 0.025 is the best answer here. So we end up with two significant figures. Remember that leading zeros are not significant. The next question that has a mixture that has both division and addition to it. So when we have this, once again, we're going to go one step at a time and determine the answer at each step. Now, it's important that we not round off too much. If we were to round at every step, we will get round-off error, which accumulates, which creates a problem. So if we do this all the way through in our calculator, here's the calculator answer that we get without paying attention to significant figures. Let's just do this all the way through, and we'll get 100.81677 as our calculator answer. But we have to look at this and determine how precise should this be. And so we need to go back and do this one step at a time. And so the first thing that we'll do is we will divide this first number. When we divide 8.6511 by 0.8827, we will get 98.00725. That's our calculator answer without rounding. Now, as I look at this, though, I'm dividing, so I ask how many significant figures? Well, the numerator has 5 significant figures and the denominator has 4. So this is limited to 4 significant figures because there are only 4 significant figures in the denominator. So let me underline those significant figures. 1, 2, 3, 4. This has 4 significant figures. And this, therefore, is precise to the 1/100th place. Whenever we look at this second number, when we divide 4.72 by 1.68, we get 2.80925. And again, I have 3 sig figs divided by 3 sig figs. I count significant figures, and this has 3 significant figures. And we are once again precise to the 1/100th place. So when we add these two numbers together, we will be precise to the 1/100th place. Remember, when we add, we don't ask how many significant figures. We ask how precise is it. And I have underlined the significant figures. I keep the other numbers so that we will avoid round-off error. But I underline the significant figures. This is precise to the 1/100th place. This is precise to the 1/100th place. So the answer is precise to the 1/100th place. The answer is 100.82. So we will round this up. We're dropping the 677. We round this up. We get 100.82. Notice we end up with an answer that has 5 significant figures. And we didn't get that by counting significant figures. Anytime adding and subtracting are involved, you can't just count significant figures. So what we did in order to get this was to say that in the numerator, we have 5 significant figures, and in the denominator, we have 4. So when we do this first division, there's 4 significant figures, or it's precise to the 1/100th place. This has 3 significant figures. It's also precise to the 1/100th place. When we add these, it's precise to the 1/100th place. Okay, let's do one more of these combined problems where we're combining addition, subtraction, multiplication, and division. So in this case, I'm going to do this all the way through in my calculator to get a calculator answer. And the calculator answer that I get whenever I do this all the way through is 0.46734,368. This is the calculator answer. Okay, so how would we express this? Well, I've got to go back and do this one step at a time, applying the appropriate rules at each step. So first I'm going to divide this. When I divide this number, I get 1.95244, that's a 9, 244,755, minus, when I divide this number, I get 1.485, 10387. Now let's go back to this. When I divide, what question do I ask? When you multiply or divide, you ask how many significant figures. The numerator has 4 significant figures. The denominator has 3 significant figures. And so I'm limited to 3 significant figures. I'm going to underline them. 1, 2, 3. This number has 3 significant figures. The rest of this is garbage, but I keep it in order to avoid round-off error. In the second number, I have 5 significant figures divided by 4 significant figures. I'm going to have 4 significant figures. There's fewer significant figures with the 4. So 1, 2, 3, 4. Now, when we subtract, we don't ask how many significant figures. We ask how precise is it. So how precise is this number? It's precise to the 1/100th place. Remember, I'm not counting all of this. This is garbage. This only has 3 significant figures. This second number is precise to the 1/1000th place. Which is less precise? That is, which is bigger, 1/100th or 1/1000th? Well, 1/100th is less precise than 1/1000th. And so we're limited to the 1/100th place. And so we drop off the rest, and whenever we round this, we have to round up because what we're dropping off here is 5 or higher, this leftmost digit. And so this will end up being 0.47. And notice that we end up with 2 significant figures in this case. 2 significant figures. You can't get that just by counting significant figures. This has 4 sig figs, this has 3, this has 5 sig figs, this has 4, and yet the answer has 2 significant figures. You have to go through the step-by-step process in order to do it. Okay, let's look at question number 5. In question number 5, we're adding a series of numbers using scientific notation. Now, when we add, we always ask, how precise is it? And to figure out how precise it is, scientific notation, remember, it changes the value of each place. So that using scientific notation, this, which is normally the ones place, it becomes the 10 to the minus 7 place. And as we count down to go to see how precise this is, then we're going to become increasingly smaller by a power of 10. This is 10 to the negative 7, 10 to the negative 8, 10 to the negative 9, 10 to the negative 10, 10 to the negative 11. So this number is precise to the 10 to the negative 11 place. The next numbers, the 6, which is normally in the ones place, but the scientific notation tells us that now this represents 10 to the negative 6. That's the value of that new placeholder. And so this is the 10 to the negative 8. We count down in a negative direction. Negative 6, negative 7, negative 8. The 3 right here, which is normally the ones place, the scientific notation tells us now it's 10 to the negative 6 place. So negative 6, negative 7, negative 8, negative 9. This is the 10 to the negative 10 place. Now we want to go ahead and do this all the way through in our calculator to get a calculator answer. And our calculator answer is 1.017587 times 10 to the negative 5. That's our calculator answer. Your calculator does not know significant figures. You have to go through the process in order to determine it. Now, as I look at this, how precise should the answer be? Well, it will be the least precise spot. Least precise means the biggest. 10 to the minus 8 is the least precise value listed. And so when we do this with looking for the least precise, I'll be precise to 10 to the negative 8. So where's the 10 to the negative 8? Well, remember with scientific notation, this, which was the ones place, this is now the 10 to the negative 5 place. And we count down in a negative direction. Negative 5, negative 6, negative 7. This is the negative 8 right here. This is 10 to the negative 8. And so we're going to drop off this. We will round up. And so the answer in this case ends up being 1.018 times 10 to the negative 5. Remember, because adding and or subtraction was involved here, you cannot just count significant figures. Too many students will say this has 5 sig figs, this has 3, this has 5, and therefore the answer must have 3. The answer doesn't have 3 sig figs. The answer has 4. And when you add, you don't even ask how many significant figures. You ask how precise, and you're limited to the least precise place. Okay, let's go to the next page to question number 6. Question number 6. Once again, this is a question involving scientific notation. So how precise is this number? Well, the 7 is in the 10 to the negative 7 place. We know that because scientific notation tells us. It assigns a new value to what was normally the ones place. The 8 then is in the 10 to the negative 8 place. So we're counting in a negative direction, negative 7, negative 8. The 8 in this number is precise to the 10 to the negative 6 place. We're told that by this scientific exponential term, the exponential term in scientific notation. So this is negative 6, negative 7. This is the 10 to the negative 8 place. And here, the 9 is in the 10 to the negative 5 place, 5, 6, 7. This is precise to the 10 to the negative 8. So each of these are precise to 10 to the negative 8. The answer will be precise to the 10 to the negative 8 place. Now there's a problem with this when we do this in our calculator. Remember, your calculator does not know it does not know significant figures. You do scientific notation in your calculator, but your calculator does not know significant figures. Your calculator gives you 1.087 times 10 to the negative 4. Now, I know the answer is precise to the 10 to the negative 8. That's how precise each of these numbers is. Well, where's the 10 to the negative 8 place in this number? Well, the ones place, scientific notation changes this to 10 to the negative 4. Negative 5, 10 to the negative 6. This is the 10 to the negative 7 place. And your calculator stopped there because it doesn't know significant figures. To get to the 10 to the negative 8 place, we have to supply another digit, a 0 here. This is the 10 to the negative 8 place. And so this number ends up being, the correct answer here, 1.0870 times 10 to the negative 4. Now, once again, you end up with a number that has a different number of significant figures than any of these. This has 5 significant figures, 1, 2, 3, 4, 5. And yet, when we look at this, this has 2 sig figs, this has 3 significant figures, this has 4 significant figures. It is possible when you add or subtract to end up with more significant figures than you started with or with fewer significant figures. And so that's important to keep in mind. Be sure you practice this kind of significant figures problem. The next kind of problem that we work in Chapter 1 is called dimensional analysis. You will find this approach very helpful, not only in chemistry, but also in your physics and in your engineering classes. You have to know how to do unit conversions. And I strongly urge you to get into the habit of doing all of your unit conversion problems this way. You cannot go wrong, and it will make problems much easier if you'll do first these 3 steps. First of all, you want to write down what you want to know. You want to write down what you want to know. And I'll illustrate what I mean. Secondly, you start with the given measured quantity. Start with the given measured quantity. And third, you apply conversion factors in order to cancel unwanted units. So you start with the given measured quantity. Number 3, you apply conversion factors to cancel unwanted units. Okay, so let's go through this. First of all, write down what you want to know. If you're doing a unit conversion, if you're doing a dimensional analysis problem, where this says write down what you want to know, all that means is look at the unit you're looking for. I'm looking for this. I want to convert this to picometers. So I'm going to write the number sign and the unit picometers on the left side of the equal sign. That's what I mean by step number 1. Write down what you want to know. The number of picometers equals. I'm going to start with the given measured quantity, which is 0.0921 nanometers. Now, in dimensional analysis, you have to write the unit down. So number 2, start with the given measured quantity. These are the first 2 steps. Number 3, apply conversion factors to cancel unwanted units. I don't want it in nanometers, I want it in picometers. So I'm going to say times, draw a line, and put nanometers in the denominator. So a conversion factor is an equality, and you have to memorize the metric prefixes. And the metric prefix nano means 10 to the negative 9. Nano means 10 to the negative 9. And so that means that I'm going to say that 1 nanometer equals 10 to the negative 9 meters. Now you memorize that nano means times 10 to the negative 9, and you always put this exponential term with the base unit, with the unit that does not have a prefix, because nano means 10 to the negative 9. Nano is the same as saying 10 to the negative 9. So the unit nanometer cancels, and I have it in meters, but I want it in picometers. So I'm going to say times, draw a line. I want to cancel meters, so I bring it down to the denominator so it will cancel. And I want to go from meters to picometers. You have to memorize what these metric prefix means. And pico means 10 to the negative 12. Pico means 10 to the negative 12. And so where would I put the 10 to the negative 12? Well, if pico means 10 to the negative 12, then 1 picometer equals 10 to the negative 12 meters. The easy way to remember this is you memorize the exponential term, and you always put the exponential term with the base unit, with the unit without the prefix. And now meters cancels, and I have it in picometers. When you do this in your calculator, everything in your numerator you multiply, everything in the denominator you divide, and you ignore ones. So I would enter 0.0921 times 10 to the negative 9 divided by 10 to the negative 12 equals, and you'll get 92.1 picometers. 92.1 picometers. Now there is one shortcut that you can do here. Now you have to be careful with shortcuts. Sometimes shortcuts get you in trouble. But one shortcut will save you a step. Let's see, I don't have much room to write it here, but I'm going to write it in smaller print here. I want what I want to know the number of picometers. I'm going to go through this again, showing you a shortcut. I'm going to start with the given measure quantity, but here's my shortcut. Instead of writing nanometers, I don't want it in nanometers, I want it in picometers. I can write 0.0921, and instead of writing nano, write down what nano means. Nano means times 10 to the negative 9 meters. And now you only have to go from meters to picometers. And pico means 10 to the negative 12, so I'll put 10 to the negative 12 in the denominator. And meters cancels 10 to the negative 12, and we'll get the answer, 92.1 picometers. So that's a shortcut that's useful, where instead of writing, you don't want it in nanometers, so instead of writing nanometers, just write nano means times 10 to the negative 9, and so you can include that. Okay, question number 8. We're going to convert 122 milligrams per deciliter to grams per liter. Okay, so let's follow the same 3 steps that we looked at before. The 3 steps are: number 1, write down what you want to know; number 2, start with the given measured quantity; and number 3, apply conversion factor. So what do I want to know? I want to know, put the number sign and the unit you're looking for. I want to know the number of grams per liter. Now here's a dumb suggestion for you that will help you when you're solving this kind of problem. My dumb suggestion for you is, if you have a combined unit or a compound unit, grams per liter, instead of writing a slash, write a horizontal line. It's easier to keep track of the units. Write a horizontal line. So I want to know the number of grams per liter. I'm going to start with the given measure quantity, 122 milligrams per deciliter. Now when I write this, write it with a horizontal line, not a dashed line. It's easier to keep track of the units, milligrams per deciliter. Okay? And I'll say times and draw a line. So number 1, write down what you want to know. All I mean is write the number sign and the unit you're looking for. I'm looking for grams per liter. Number 2, start with the given measure quantity. Write the entire quantity, including the unit. Number 3, apply conversion factor. So let's focus on milligrams first. I don't want it in milligrams. I want it in grams. And so I'm going to put in the denominator milligrams to grams. Now, you have to memorize the table of metric prefixes. You have to know what milli means. Milli means 10 to the power of negative 3. So where does 10 to the negative 3 go? The exponential term always goes with the base unit, with the unit without the prefix. 10 to the negative 3 grams equals 1 milligram, because milli means 10 to the negative 3. This is just a different way of writing milligram. Milligram is 10 to the negative 3 grams. So milligrams cancels, and I have it in units of grams in the numerator per deciliter. So we're halfway there. Now I don't want deciliters in the denominator, I want liters. So I'll say times, draw a line, and I'll put deciliters in the numerator and go from deciliters to liters. Now you have to know what deci means. And I always think of decimating. In ancient Greece, if you decimated an army, that meant that you killed 1/10 of the army. Deci means 1/10. Deci means 10 to the negative 1. 1 deciliter is equal to 10 to the negative 1 liter. The exponential term that you memorize goes with the base unit, 10 to the negative 1 liters. So deciliter appears in the numerator. It cancels deciliters in the denominator. So everything in the numerator you multiply, everything in the denominator you divide, you ignore ones. 1.22 times 10 to the negative 3 divided by 10 to the negative 1 equals 1.22 grams per liter. Now, since all we're doing is multiplying and dividing, significant figures is easy. This has 3 significant figures. This is exact. This is exact. So our answer ends up with 3 significant figures. We end up with 1.22 grams per liter. So this is a dimensional analysis problem. The next problem, problem number 9, is also a dimensional analysis problem, but this has an added twist in it of having a squared term, centimeters squared and square inches. And so this is a different type of problem that you have to be careful about. So number 1, write down what you want to know. I want to know the number of square inches. So the number of inches squared equals. Now, let's think about, what do you have to know? There are lots of conversion factors, and I want you to know 2 conversion factors between the English system and the metric system. I want you to know that 2.54 centimeters is equal to 1 inch, and that's exact, and that means there's an infinite number of significant figures. This will not limit the number of significant figures in a calculation, so you have to know centimeters to inch. I also want you to know pounds to kilograms. There are 2.205 pounds equivalent to 1 kilogram. at least at sea level. That's true at sea level. This has 4 significant figures, which is generally all that we will need. So I want you to know those conversion factors. I also want you to know 12 inches equals 1 foot, and I want you to know that 1 milliliter is exactly equal to 1 cubic centimeter. It's just a different way of saying the same thing. So here are the conversion factors you have to know. Now you also need to know the table of metric prefixes. So if you know the table of prefixes and you know these conversion factors, you can solve any problem, and any other conversion factor that you need will be given to you. So I want to know the number of square inches. I'm going to start with the given measured quantity. The given measured quantity is 27.2 centimeters squared. So I'm going to say times, draw a line. And to go from centimeters squared to inches squared, I'm going to use this top conversion factor. 2.54 centimeters equals 1 inch. So I'm going to put down in the denominator, I'm going to put 2.54 centimeters equals 1 inch. Now, the reason that I'm doing this problem that involves a squared unit, there's no square on this unit, 2.54 centimeters equals 1 inch, is if you have to square a unit, you can't just square the units, you have to square the entire value. 1 square inch is not equal to 2.54 square centimeters. However, 1 square inch is equal to 2.54 times 2.54 centimeters squared centimeters. So that's what you have to do. You have to, if you square the unit, you have to square the conversion factor as well. So when you do this, we'll have 3 significant figures. We will get 4.22 square inches. 4.22 square inches. This has 3 significant figures. This is exact, so we'll have 3 significant figures. 4.22 square inches. So remember to square the 2.54. Now, let's look at another problem that I could have asked about this. I could have asked, how many square feet? How many square feet? It should be square feet. Okay, so let's do that. We'll just set this up and do this as a simple example problem. And I want to know the number of square feet. If I were to start with 27.2 centimeters squared, and first I go from centimeters to inch, I know 1 inch is equal to 2.54 centimeters. Well, if 1 inch equals 2.54 centimeters, is it also true that 1 square inch equals 2.54 square centimeters? And the answer is heck no. You can't just square or cube the unit. You have to square or cube the entire quantity. So it's this whole quantity squared. So now we have square centimeters cancels, and I have square inches. So I want you to know that there are 12 inches equal to 1 foot. And the other English conversion factors I'll give to you, and I'll show you that in just a minute. So I'm going to put in the denominator 12 inches equals 1 foot. But this is square inches, so if 1 foot is equal to 12 inches, is 1 square foot equal to 12 square inches? And the answer is heck no. You have to square the whole quantity, not just the unit. 1 square foot is equal to 12 times 12 square inches. Okay, so whenever we do that, that's going to cancel out the unit of inches, and we'll end up, if we were to have this question, with 0.0293 square feet. 0.0293 square feet. Okay, so be sure you know how to do squaring and cubing. Number 10 is another example of doing a problem that involves squared and cubed values. This says pure gold has a density of 18.9 grams per cubic centimeter. Express this in units of pounds per cubic feet. So I'm going to still be using, let's pull this sheet down a little bit so that we can still see these conversion factors at the top. I'm still going to be using these conversion factors that I asked you to know up here. So I want to know the number of pounds per cubic foot. Now my dumb suggestion here is, instead of writing a slash line, write a horizontal line. Number 1, write down what you want to know. I want to know the number of pounds per cubic feet. If you'll get in the habit of solving dimensional analysis problems this way, this will help you in physics, this will help you in your engineering courses when you're doing unit conversions. Write down what you want to know. The reason we write this down, it helps us at times to keep looking back and to see what do we need to get. Number 2, start with the given measured quantity, 18.9 grams per cubic centimeters. 18.9 grams per cubic centimeters. And again, Don't write it with a slash line. Write it with a horizontal line. It's easier to keep track of the units. So I've got to change these units. First, let's focus on the numerator. I need to change grams to pounds. Okay, and so the conversion factor that I know up here is that 1 kilogram is equal to 2.205 pounds. 1 kilogram is 2.205 pounds. So first of all, let's get this into kilograms. I'm going to say times, draw a line, and go from grams to kilograms. Now the prefix K, kilo, means 10 to the power of 3. So we always put the exponential term with the base unit, with the unit that does not have a prefix. So 1 kilogram is equal to 10 to the power of 3 grams. That allows us to cancel the unit grams. So we have kilograms per grams. There's 10 to the power of 3. So I need to do one more thing to get it in pounds. I'm going to say times, draw a line, put kilograms in the denominator and pounds in the numerator, so that the one conversion factor you need to know in terms of mass is that 1 kilogram is equal to 2.205 pounds. 1 kilogram is equal to 2.205 pounds. Okay, so that gets us into units of pounds. That gets us into units of pounds, but it's pounds per cubic centimeter. We need it in pounds per cubic foot. So we're going to say times, draw a line. I don't want it in cubic centimeters. I want it in cubic feet. So what I can do is I can go from centimeters to inches, and then from inches to feet. First, let's go from centimeters to inch. I put centimeters up in the numerator, so it'll cancel the cubic centimeters in the denominator. And inch. And I know that you have to memorize this. 2.54 centimeters is equal to 1 inch. So if 2.54 centimeters equals 1 inch, is it also true that 2.54 cubic centimeters equals 1 cubic inch? And the answer is heck no. You can't just square or cube the unit. You have to square or cube the entire quantity. 2.54 times 2.54 times 2.54 cubic centimeters is equal to 1 cubic inch. So we have to cube the entire quantity. And when we do that, that allows us to cancel out cubic centimeters. Now I have cubic inches in the denominator, but I want cubic feet. And so the conversion factor you have to know that 12 inches equals 1 foot. And so I'm going to bring inches up into the numerator. 12 inches is equal to 1 foot. Well, if 12 inches is equal to 1 foot, is it also true that 12 cubic inches equals 1 cubic foot? This is a cubic inch. The answer is heck no. Heck no, you can't just square or cube the unit. You have to square or cube the entire quantity. If the unit was not squared or cubed to begin with, and you have to square or cube it, then you have to square or cube the entire quantity. 12 times 12 times 12 cubic inches is equal to 1 cubic foot. Okay, so that cancels out cubic inches, and now I have cubic feet in the denominator. So you need to do this in your calculator. Make sure you get the correct answer in your calculator. This has 3 sig figs. This is exact. This has 4 sig figs. This is exact, and this is exact. And so the number of pounds per cubic feet calculates out to be, to 3 significant figures, 1,180 pounds per cubic feet. I can go back to writing this as a slash line. Now I'm done with the calculation. There'll be 3 significant figures. Remember, a 0 at the end of a number that does not have a decimal place is not significant. So this has 3 significant figures. If we want to, we can write this using scientific notation to emphasize that there's 3 significant figures. 1.18 times 10 to the power of 3 pounds per cubic foot. Okay, that was number 10. Next, let's go to number 11. Okay. Question number 11. If a molecule of gas is traveling at a velocity of 875 meters per second, how fast is it going in miles per hour? Now notice in this case, and this is an old test question, just about all of these practice questions are old exam questions. Notice that you were given in this case this conversion factor. So there are 4 conversion factors that I'm asking you to memorize. Let's put those on the screen again. Here are the 4 conversion factors that I'm asking you to memorize, plus the metric prefixes. Any other conversion factor I would give you, just as I give you this one on the exam. So I want to know the number of miles per hour. So write down number 1, write down what you want to know. I want to know the number of miles per hour. Miles per hour. The abbreviation for hour is just H. The number of miles per hour. Now, my dumb suggestion is write this as a horizontal line instead of a slash line. It's easier to keep track of the units. Number 2, I start with the given measured quantity, 875 meters per second. I'm going to write this as a horizontal line rather than a slashed line. Now I want to go from meters to miles, and I'm given this conversion factor. 1 mile is equal to 1.6093 kilometers. Now there is one shortcut I can use here. Since kilo means times 10 to the power of 3, this is the same as saying 1 mile equals 1,609.3 meters. Kilo means 10 to the power of 3. And so I can immediately convert this to meters. And we could go from meters directly to miles then. So I don't want it in meters. I'm going to bring meters to the denominator. And I know that 1 mile is equivalent to 1,609.3 meters. Okay, so I get this from the conversion factor. You're not expected to memorize this conversion factor. I got this from the conversion factor. And so my units of meters cancel, and I have it in miles, but it's in miles per second, so I need to go from miles per second to miles per hour. And so I'm going to bring seconds up to the numerator, and I know that 1 hour contains 60 times 60 seconds. 1 hour contains 3,600 seconds per hour. So the unit, I messed up. Hours in the, no, that's correct. Seconds is in the denominator. I want to cancel it, so I'll bring this up to the numerator. And so we cancel the unit of seconds, and now we have it in miles per hour. Whenever we calculate this out, we will get 1,960 miles per hour. And this has 3 significant figures because this had 3 significant figures. Okay, so we've done significant figures, we've done dimensional analysis. There's a few other random examples that I want to show you. One has to do with density. You have to understand what density is. Now there's 2 ways to solve density problems. One way is to solve it using a plug-and-chug type problem. You need to know that density is defined as the mass per volume. Density is defined as mass per volume. If you know any 2 of the 3, you can solve for the third. So let's list the information that we're given. We have an empty Erlenmeyer flask. So here's an Erlenmeyer flask. And if it's empty, it has a mass of 144.5 grams. That's the empty flask. That's the empty flask. But when it's filled completely with water, so we're going to fill this completely with water. So I'm going to shade this in to indicate that it's completely filled with water. Then the total mass is 219.4 grams. That's the flask plus the water. Flask plus the water. Okay. Now, if this is the mass of the empty flask, this is the mass of the flask plus the water, then therefore we know the mass of the water. The mass of the water is equal to 219.4 grams. That's the total mass minus the mass of the empty flask, 144.5 grams. Now, don't count sig figs. If you're subtracting, you don't ask how many significant figures. You ask how precise is it. Each of these is precise to the 1/10th place. And when we subtract these, we get 74.9 grams. Notice we're immediately down to 3 significant figures, even though our 2 values here have 4 significant figures. So this is the mass of the water. Now this says, if we take the water out and we fill it with chloroform, and here's the density of chloroform, what is the total mass of the flask and its contents when the flask is filled with chloroform? Well, let's think about what's going on here. The key to solving this problem, is knowing that if we were not given the volume of the flask, we were just given the mass. We were not given the volume of the flask, we were given just the mass. And so we can determine the volume of the container by determining the volume of the water that it will hold. we determine the volume of the container by determining the volume of water that it will hold. Okay, so let's look at that and do that. So we have this formula: density is equal to mass over volume. Since density is equal to mass over volume, I can rewrite this to say the density of water, and in chemistry for some reason we write everything as a subscript, and we say the density of water is equal to the mass of the water, right, this is a subscript, over the volume of the water. Now I know that that's redundant, but we know the density of water and we know the mass of the water. We can find the volume of the water. So we rearrange and solve for the volume of the water. The volume of the water is equal to the density of the water times the mass of the water. I'm sorry, the density of the water divided by, if I rearrange, I'm just going to swap these up. Volume comes up and density comes down here. And so volume is equal to, let's rewrite this. I wrote this incorrectly. Volume, when I rearrange this equation, volume is equal to mass over density. Volume is equal to mass over density. And so the volume of the water is equal to the mass of the water, is equal to mass of the water over the density of the water. So the volume of the water is equal to the mass, 74.9 grams, divided by the density of water. We're given that the density of water is 1 gram per cubic centimeter. And so the volume of water is 74.9 cubic centimeters. Okay, now the key point here is if this will hold 74.9 cubic centimeters of water when it's completely full, then that means that that's the volume of the flask. That's all it will hold of anything. It will hold 74.9 cubic centimeters of anything. And therefore, when we fill it completely with chloroform, the volume of the chloroform, let's just abbreviate, or let's just write, the volume of the chloroform is also, when we fill this up, 74.9 cubic centimeters. So I know the volume of chloroform. I know the density of chloroform. I can find the mass of chloroform. So by rearranging this equation, mass is equal to density times volume. Mass is equal to density times volume. So I know the volume. I can calculate the mass. Density equals mass over volume, and therefore the mass equals the density times the volume. The density of chloroform is 1.48 grams per cubic centimeter, and the volume of the chloroform is the same as the volume of the water because that's all that the flask will hold, 74.9 cubic centimeters. The unit cubic centimeters cancels, we end up in grams, and the mass of the chloroform equals, when we multiply this out, we get 110.85 grams of chloroform. Now I'm going to keep that number. We don't want to round until the very end to avoid round-off error, but there are only 3 significant figures here. There are only 3 significant figures here. Now, when you answer a question, always be sure you answer the question that was asked. The question says, what is the total mass of the flask and its contents when the flask is filled with chloroform? What is the total mass of the flask and its contents when it's filled with chloroform? And so, therefore, the total mass is equal to the mass of the chloroform, 110.85 grams, and again this has 3 significant figures, plus the mass of the empty flask, 144.5 grams. Now when we add, we have to ask how precise is it? And this is precise to the 1/10th place. This is only precise to the ones place, so we're limited to the ones place. And so when we add these two together, limited to the ones place, we will get 255 grams. 255 grams. That's the total mass of the flask and the container. Okay, let's look at number 13. Number 13 asks, the density of mercury is 13.6 grams per milliliter. What is the mass in pounds of 10 cubic feet of mercury? Now, we're given the density, and we're asked, what is the mass in pounds of 10 cubic feet of mercury? Now, any density problem, as we saw in the problem just up above, can be solved as a plug-and-chug problem. We have a formula. If you know two of the three variables, you can solve for the third. But we can also use density as a conversion factor, and that will save us time often. Density can be used as a conversion factor. So the shortcut for solving this problem, it's faster to solve this using this as a dimensional analysis problem and using this as a conversion factor than it is to do a plug-and-chug problem. Okay, so I'm going to go through the steps that we've said over and over, the three steps. It's the three steps that we had written back on the previous page. Write down what you want to know, start with the given measured quantity, apply conversion factors to cancel unwanted units. So when I write down what do I want to know, I want to know the number of pounds of the number of pounds. I want to know the number of pounds. What is the mass in pounds? Number two, I start with the given measured quantity. Now notice in this case we have two numbers. So which one do I start with? Well, when I say start with the given measured quantity, that means you never, never, never start with a conversion factor. I have two numbers. I'm going to use density as a conversion factor, so I don't start with the conversion factor. I start with this number, the 10 cubic feet. So we're going to have 10 cubic feet. Now, density of mercury is 13.6 grams per milliliter, or we could say the density is 13.6 grams per cubic centimeter. Remember that another way to say milliliter is cubic centimeter. They're perfectly interchangeable. So I need to get cubic feet into cubic centimeters so that I can use this as a conversion factor. I need to get cubic feet into cubic centimeters. So the way I'm going to do that is I'm going to go, first of all, from feet to inches, and then I'm going to go from inches to centimeters. So to go from feet to inches, I know that 12 inches is equal to 1 foot. Now this is cubic feet, so I have to cube the whole quantity. Remember, you can't just square or cube a unit if it's not originally squared or cubed. You have to square or cube the entire quantity. So I'm going to cube this. Okay. So now I have cubic inches. Now I have to memorize that 2.54 centimeters equals 1 inch. And I have to cube this entire quantity. So when we do this, cubic feet cancels and cubic inches cancels, and I have it in cubic centimeters. So here's where I can use density as a conversion factor. This says that there are 13.6 grams of mercury in 1 cubic centimeter of mercury. So here's the step where we're using density as a conversion factor. And so that allows us to cancel the unit cubic centimeters, and now I have it in grams. Well, I want to go from grams to pounds. Now my conversion factor for grams to pounds, if I just write that over here, is 2.205 pounds equals 1 kilogram. Now a shortcut here is I know that a kilogram is 10 to the power of 3 grams, or 1,000 grams. That is 2.205 pounds is equal to 1,000 grams. So a shortcut, I can just go from grams to pounds. If I go grams to pounds, I know that there are 2.205 pounds per every 1,000 grams, which is a kilogram. So the unit of grams cancels. Now I have it in units of pounds. So how much would 10 cubic feet of mercury weigh? It would weigh, in pounds, 8,490 pounds. I rounded this to 3 significant figures, because this has 3 significant figures. This is exact, This has 3 significant figures. So this has 4 significant figures. So we're limited to 3 significant figures. This could be written using scientific notation, 8.49 times 10 to the power 3 pounds. Remember, when in science, anytime you give an answer, you don't just give the number. You have to get to the correct number of significant figures, and you must include the unit as well. You must include the unit as well. Okay? Next, number 14. This is another similar conversion where we're going to convert a cube term. I'm going to go from cubic micrometers to cubic millimeters. Cubic micrometers to cubic millimeters. So this illustrates this. It's the kind of question you can be prepared for on the first exam. I want to know the number of cubic millimeters. Number 1, write down what you want to know. I want to know the number of cubic millimeters. Number 2, start with the given measured quantity. The given measured quantity is 2.25. Now this prefix is micro, cubic micrometers. So I don't want it cubic micrometers, I want it in millimeters. So first I'm going to go from micrometer to meter. First I'm going to go from micrometer to meter. And here's where you have to know the metric prefixes. The metric prefixes are that milli means 10 to the negative 3, and micro means 10 to the negative 6. So micro, which we write, it looks like the letter U, but it's got a tail on the front end, 10 to the negative 6. So micro means 10 to the negative 6. So where does 10 to the negative 6 go, in the numerator or in the denominator? If you're changing metric prefixes, the exponential term always goes with the base unit. 10 to the negative 6 meters is equal to 1 micrometer, because micro means 10 to the negative 6. Okay, so that's micrometer, but this is micrometer cubed. I have to cube the entire quantity in order to get this to work. So you have to cube the entire quantity. Now be sure you're checking this on your calculator to be sure you're getting the correct answer. Next, we're going to go from meters to millimeters. This is why I write down what I want to know. It guides me forward. I have it in cubic meters. I want to go from cubic meters to cubic millimeters. So meters to millimeters. Now, milli means 10 to the negative 3. So where does 10 to the negative 3 go? It goes with the unprefixed unit. 1 millimeter is equal to 10 to the negative 3 meters. And then I have to cube that entire quantity. So now, cubic meters cancels cubic meters, and I have it in cubic millimeters. And this question calculates out to be 2.25 times 10 to the negative 9 cubic millimeters. Okay, and the last 2 questions ask us to convert from Kelvin to degree C to Fahrenheit, and from Fahrenheit to Celsius and to Kelvin. So you have to know how to do this. Now, just a short reminder of how you can remember this and always keep this straight. You can easily remember this over here by thinking of the temperature scale. If I put the temperature scale in Celsius over here and in Fahrenheit over here, the freezing point of water in Celsius is 0 degrees C. The boiling point of water in Celsius is 100 degrees C. In Fahrenheit, the freezing point of water is 32 degrees Fahrenheit. The boiling point of water in Fahrenheit is 212 degrees Fahrenheit. Now, the difference from the freezing to the boiling point in Celsius is 100 degrees C. The difference from freezing point to boiling point in Fahrenheit is 180 degrees Fahrenheit. Now, that means that a degree C is larger than a Fahrenheit. There are only 100 degrees here, whereas there's 180. And the ratio, 180 to 100, that ratio calculates out down to be 9 to 5. That's a ratio of 9 to 5. Now, since a Fahrenheit, the size of a Fahrenheit is larger than each Fahrenheit, the ratio here is 9/5. And the relationship then is going to be that the temperature in Fahrenheit is equal to 9/5 times the temperature in degrees C plus 32 degrees. And to go back in the other direction, Celsius is equal to 5/9, and this is a quantity here, Fahrenheit minus 32. Fahrenheit minus 32. Okay, so those are the relationships that we're going to use to solve this problem. First, I have this in Kelvin. Let's go from Kelvin to Celsius. And you need to know that the temperature in Kelvin is equal to degrees C plus 273.15. We normally use Celsius in science, but you need to be able to put it in the SI unit of Kelvin. And so the temperature in degrees C is equal to Kelvin minus 273.15. That is, the temperature in Kelvin is 355 minus 273.15. Now, the 273.15 is exact. It doesn't limit the number of significant figures. But when we do this, we're subtracting, so counting significant figures, we're precise to the ones place. And so this calculates out to be to the ones place. And this calculates out to be 82 degrees. 82 degrees C. I only have two significant figures. So 355 Kelvin. Now, when we write Kelvin, we don't write a degree sign. 355 Kelvin equals 82 degrees C. Now that we have it in Celsius, we can convert it to Fahrenheit using this relationship. So the degrees Fahrenheit, the temperature in Fahrenheit, is equal to 9/5 times the temperature in degrees C plus 32. We add 32 because that's at the freezing point. The 0 point of Kelvin is 32 degrees for Fahrenheit. Okay, so this will be 9/5 times, and the temperature in Celsius is the 82 degrees C plus 32. And when we calculate this out, we will get the temperature in Fahrenheit to be 180 degrees Fahrenheit. So this is equal to 180 degrees Fahrenheit. So be sure you can do that conversion. Now, to convert Fahrenheit to Celsius and then to Kelvin, first we'll go from Fahrenheit to Celsius. And we use the relationship that the temperature in Celsius is equal to 5/9 times the temperature in Fahrenheit minus 32. So 5/9 times, and the temperature in Fahrenheit is 103 minus 32. And when we calculate that out, the temperature in degrees C will be 39 degrees C. And the temperature in Kelvin then, Kelvin is equal to the temperature in degrees C plus 273.15. That's 39 plus 273.15. And that calculates out to be 312 Kelvin.